Welcome, everyone, to my talk about dependencies and Kotlin Native. My name is Tadeas Kriz, and we'll jump right into what we'll talk about. So for our agenda today, we'll be talking about the differences and similarities of dependency management, compilation, and perhaps linking, and execution between JVM and native, between those two worlds, and how they impact Kotlin Native, and then look at some common problems and their solutions or workarounds, whatever you want to call them. So a little bit about me. Again, Tadeas Kriz. I've been doing mobile for many, many years. Now I'm a senior mobile developer at TouchLab. But when I started, my kind of career journey went from PHP, C#, Java. So I was all in that managed memory world for most of my life before I started iOS. And I went into iOS when it was still Objective-C, so no Swift. And I dove head first into the native world, not really knowing anything about native because I didn't have any computer science education back then. And so all of those things that I'm going to be explaining now, to some of you, they may be super simple. To anyone who never done native, they may feel the same, like lost as I was. So I want to help with that. And we'll go to comparisons first, because I'm hoping that even though most of you probably know how JVM works, how the internals work, hopefully you know, it's always good to take a look at it and then see how it works on the other side. We'll start with JVM because I wanted to put them side by side, but honestly, I would not be able to fit them on the slides to compare. So we'll go to JVM first, then native, and then we'll apply all those things to Kotlin Native. So in the JVM world, we have many dependency management solutions. We have Maven, we have Gradle, some of you may remember Ivy. But all in all they do is kind of the same thing. They go and fetch jar files. In Android case, it's a little bit different file, but it's basically the same thing still. So in here, we have a very simple example where we grab two dependencies, A and B, from somewhere. We don't really care from where. So as I mentioned, those are just two jar files, right? They don't have any transitive dependencies here. If they had, it would be way more files. And for our example here, we don't really care about the group or the version, so I'm going to simplify the name just to A and B.jar. So then the compilation. And I want to put in a disclaimer. This is simplified. If we are talking about really what's going on, we would be here for way longer, and it would not be a presentation. That's for sure. So with the compilation process, we start with our dependencies. So we have those jar files. But inside of those are actually class files, that's the bytecode. That's what was compiled from other Java and Kotlin classes. And then our Kotlin or Java code, whatever you use, hopefully Kotlin at KotlinConf, depends on those classes and those declarations in those class files. And then compiles into our own class file. So then, once we're ready, usually with other class files in our project, we bundle everything into a jar file of our own. And those jar files, all three of them, become our class pod when we're executing. So all of the classes are available for the JVM machine and loads those classes in them. Because jar files are just archives, we can actually take all of the class files and put them into a single one, having a single file for the class pod. This will be something I'll reference to later on in the native, where it's not as simple. Coming to the native now, and again, a disclaimer, there will be many of those. KMP, when you think of KMP, it's usually Android and iOS, right? Maybe some other Darwin platforms, macOS, watchOS. You can target Linux and Windows in native, not just JVM. Those are similar to Darwin in the native world, but there are slight differences. Comparing all of them, again, we would be here way too long, so we'll be looking at Darwin, because that's the iOS and macOS. So starting with dependency management again, already we'll see that it's not as simple as in JVM world, where all of the management does is it gives us the jar files. We have multiple dependency managers to choose from. 2 out of 3 are deprecated basically by now, CocoaPods and Carthage. Carthage may not think that they are deprecated, but no one is essentially using them anymore. But whether you use CocoaPods, Carthage, or Swift Package Manager, in the end, you get something. And unless you go and look what you're getting, you don't know what it is, right? So in JVM, we already established you get the jar file, and you can be kind of sure that it's going to be a jar file. In native, especially iOS, we get something, and that something can either be a pre-built or also called a vendored framework, and that can contain either a static or dynamic library, which we'll get to soon, or a source package. Now, notice that I'm using C and H here for files. We will be talking specifically about C, because C is like as low as you can get while still writing source code. And because it lacks those high-level functions, we don't have to deal with things that don't really matter for our understanding of those differences. Whether it's the framework or the source file, we will get some header files that declare our API. That's what those dependencies provide us. So that will be our public stuff in Kotlin or Java. The compilation on native is split basically into 2 phases, compilation and linking. Compilation is done by the compiler, and it takes source files and headers and everything in between and produces an object file, which is machine code, but it is not executable code. So you can't really take an object file and just say, please run this. That will not work. It has these undefined symbol references, which are basically pointers to things that you don't have in your file. So your source code, if you think of your class in Kotlin, whenever you use other class, that would be an undefined reference somewhere else. You don't know where it is, you just know that it should exist, and it should have this name. So with that, let's take a look at visual, how it all is put together. We have the dependencies. At this point, we do not care what they are. All we care about is that they give us the header files. And then we have our own header file and the C code file. Those reference the symbols declared in those headers and produce an object file. OK. I apologize for that. Can I get a bottle? That might be better, so we don't have those visual audio effects. So, thank you very much. Before we move on, I want to talk about what are symbols. Because symbols, when I started native, I was super confused about what symbols are, because they are kind of everything and nothing. Like, everything is a symbol in native. So let's take a look at what quote-unquote symbol is in Java. In Java, we have kind of 2 levels for symbols, right? We have the classes. So those are identified by their fully qualified name. So there will be com.example as the package name, and then A1 as the class simple name. And then inside classes, we have their members. So a function, hello world. Notice that the parentheses is bold here. It's basically part of that quote-unquote symbol. And then fields. The name of the field, again, quote-unquote symbol. In native, things are simpler and more complicated. Simpler because we don't have 2 levels. We have a single one. It's just a text, just a bunch of characters. So a C function here, its symbol is hello_world. When I mentioned in JVM that the parentheses were part of the symbol, or signature, that allows JVM to support overloading. In C, actually, how many of you either written C or are actively writing C? OK, good chunk of people. I don't know which ones were actively, and I don't want to know. That's why I asked both at the same time. So basically, in C, we cannot overload. You can have hello world take long int, but also a different one that would take a pointer. It just doesn't work like that. We have these 2, 3, 4 if we need multiple parameters, and so on. And then global variables, also symbols. And that's the name of the variable. So if we have a hello world function, we cannot have a hello world constant or a variable that's global. And then higher level languages like Objective-C, they use symbols to encode metadata about themselves. So for example, the Objective-C uses this Objective-C underscore class underscore $, underscore, and then followed by a name of a class. So for all the classes that you have, Objective-C classes that you have in your project, will have these symbols. And then the Objective-C runtime basically asks during runtime, please give me everything that starts with this prefix. And it knows that those are your classes and loads them and is able to be dynamic, even when C is static itself. And then lastly, debug information is also symbols, because everything is symbols. So like type information, in Java, classes, types are part of the whole thing. You need to know where things are stored, and the VM needs to know. But in native, type is essentially just a structure of memory. Right? It's like, here is one integer, 60, 32-bit, whatever, and there's another integer. That information is not needed once you're not debugging it. So these symbols can be stripped, and they are only needed for your debugger. Also, file names are in symbols and a bunch of other things. It's just symbols all the way down. But what are they? Can I get that water? Thank you. Thank you very much. Oh, yeah, thank you. Technical difficulties. So, as I learned native, and I've used some tools that give you like the symbol names that are in your binary, I was still confused about what it really means. Because the answer is so simple that you kind of like, everyone talks about symbols and how like complex they are sometimes. And they are very simple concepts where we have some kind of declaration. So A1 here, that's our symbol name in the header. And then in the binary, there's a symbol table, which means we have, on one hand, the names of the symbols, and on another hand, where they are in the binary. And that's basically it. So here, in this randomly generated example that means absolutely nothing, we basically have A1 has some address, and that address is somewhere in the binary. So if your code says, please call this function, what it really does is take a look at the symbol table, tell me where it's going to be, and then you basically jump there in memory. It's, again, more complicated. I'm simplifying things. The one thing I was super confused about is how C does a lot of conventions. So, and all over the native world, there's a lot of conventions. When I was thinking about calling a function in Java, in my mind, I had a function, I gave it a parameter, and it got the parameter, it starts running, and then it gives me something in return or throws an exception. Where in C world, we have different ways that the function can be called. We either use registers to give it the parameters, or we put the parameters on the stack, and then we call the function. There's so many things that are just conventions, and if you don't mind the convention, you can get into weird places and undefined behavior. But how does it all fit together? How do we know what symbols to use and how to actually like move from the object file Choose something that can run. That's where the linker comes in. It takes object files, it takes static and dynamic libraries, and then it produces either a dynamic library or an executable. It includes all the object files that you give it inside that library or executable. It includes all the static libraries that you gave it, so those are bundled in, all their symbols are bundled in. And then any dynamic libraries that you provided are kept in as so-called load commands, which basically then tell the runtime, we need these libraries. There are symbols in them that we will need. Now, can someone tell me or guess what is the result of this linking? What would be the result? What would be instead of the question mark? OK. No. The answer is we don't know. One, it depends on what we decide, what we want to be the result. But when we're talking about linking, there are two possibilities. But the other thing is we also need to know what A and B are to determine whether we can actually build B. The result. So that brings us to the difference between static and dynamic linking. Another point of confusion, maybe that's just me, maybe I'm just not that bright. Static linking is not linking. Static linking is just object files in the trench code. You basically just take all the object files that you just compiled and put them side by side in an uncompressed archive. But we still call it static linking for some reason, even though it still needs linking to be executable. That's where the dynamic is. As I mentioned, the linker, they only runs for dynamic. The final binary, whether it's a dynamic library or an executable, can depend on other dynamic libraries, and it's actually something that is essentially immutable in terms of the code that's inside of it. Now, why do we have these two things? What's the difference? One thing I want to preface this with is that as how many of you are mobile developers? OK, it's on maybe half. For mobile, most of these don't matter that much because we always deploy the whole bundle, the whole app, with all the dependencies, except for system dependencies, but those are kind of separate. So when I talk about caching, especially for mobile developers, I'm talking more about caching the input of your compilation and of your linking. So you can, because it's a final binary, you can cache it on your server and then download it, and you can work with it similar with how Maven works with jar files. In places where we have more control than on mobile, so in Linux, Windows, Mac OS, we can actually cache the dynamic library itself, so we don't have to redeploy it. If that library does not change, and if the versioning is done correctly, it's a tough sell oftentimes, the caching can, imagine a dynamic library that has a gigabyte. And you don't want to deploy it each time you're changing your small 1 megabyte application, right? With dynamic, you can just leave it where it is and run it. With static, that's not possible because you always need to include everything inside your application and make your 1 megabyte app into a 1 gigabyte app. And the same thing works with memory space. In mobile, again, we don't get to get this benefit mostly. But if you have a large dependency, 1 gigabyte, if you have 3 apps that all use it, and use it statically, you will use 3 gigabytes of RAM when those 3 are running. But if that's a dynamic dependency, they can reuse the single one that's been loaded into memory as long as it's read-only. Again, so many disclaimers that we would be here all day, all night, who knows how long. All of these things, the common API, the reusing memory space, the caching, they all stem from that thing being final, almost immutable. It also gives us the faster compilation time. And these two last points are, it depends, because if you change the dynamic library, you need to rebuild it. You don't get that faster time. So for Kotlin Multiplatform, if you make it dynamic and you're changing the Kotlin, you will not get faster compilation time just because you make it dynamic. It may actually be even slower because, again, it depends. Slower startup time works the same way. Because the dynamic libraries are separate from your main one, the dynamic loader, when you're running your app or executing, it needs to load everything. It needs to plug everything. It needs to load things that you may not even be using. So the more dynamic libraries, the more dependencies you have, the slower your app will start. But again, it depends, because this can happen with static too. It's just complicated and complex. With that in mind, we go back to the previous example. And as I said, we need to know what we're actually doing and what we have on the input. So we're going to make some assumptions. We're going to say that A is dynamic, and then we're going to say that B is static. Now, what is the output? Unless I tell you what we're building, you still can't answer that. We're building an executable. So that would be the foo on the right. Notice that the output is essentially the A. That's the same one that we've put in on the input, and then foo. B, nowhere to be found. That's because B is linked directly into foo. Now we have these two, and then the depends on arrow is our load command. So that's when we're running the executable. The dyd, which we get to here, will know, OK, I need to pick up that library, load it into memory, put things together, and then everything will work. It's important to stress here that the B is now in foo. So if instead of an executable, we are building a dynamic library, we can no longer include B in anywhere else. And we'll get to why in later part of this talk. So where does Kotlin Native fit in on all of this? Kotlin Native is a hybrid between the two. And instead of making things simpler for us, it's making things more complex, because it's taking from both, right? The complexity is not really overlapping between the two. So we're getting both. And what I like to say is that Kotlin Native produces native binaries, but when it's building, it's not really native. So for dependency management, and I don't mean this to say Kotlin Native sucks. I don't think so. I don't mean it. This is more of a Kotlin Native is so complex. This is how we often feel, for no fault of Kotlin Native itself. Well, maybe a little fault. And the reason really is that the dependency in management in Kotlin Native gives us C interop, where we can take headers from C, run it through, and it will give us klibs. But those klibs are also used for anything that library developers provide into Maven Central or other repositories. So Gradle grabs in klibs too. You can already see the parallel between, in JVM, we have a jar, and we know what jar is, and it's the same thing. Here we have a klib, and without looking into it, we don't know what it is. And then through the CocoaPods plugin, we can also go full circle. CocoaPods plugin downloads the native iOS dependency from CocoaPods. It gives the headers to cinterop. That creates the klib that we then compile. Now, this didn't fit on slide, and Keynote is either limited or my knowledge of Keynote is limited, so I wasn't able to do the nice highlight, so bear with me as we go more manually with it. So top left, we have the header file. So A, in this example, will be a native library that our Kotlin depends on. And then B will be a Kotlin native library that someone else built for us. So cinterop gives us klib from that header file. Once we are done with that, we don't need the header file anymore. We just have the Kotlin klib. From those two klibs, we get what's inside. It's no longer .class, it's IR. It's Kotlin Intermediate Representation. If you ever build a Kotlin compiler plugin, you know what IR is, and you don't like it. So then we have our Kotlin source file, and it basically references that IR, right? Those are the representation of Kotlin classes and the Kotlin representation of the C declarations. We build our Kotlin into IR, and then in turn, we take the IR and put it into klib again. So this is the compilation process. Now we should move on to linking, but Kotlin Native actually has a second compilation, and it's when we actually get the object files. Because remember, we only have klibs now. So we need an object file at the end. Start with the klibs, extract them to get the IR, and then the IR is built, compiled into the object file. Now, this is something that you usually don't think of when you're building KMP, because this whole second compilation and then the linking is called linking in Gradle. So when you're running your Gradle link task, it's actually doing compilation of klibs into object files, and then takes those object files and links them. And it's important to know this distinction, because it, at least for me, it unlocked a better understanding of what actually happens. And that the Kotlin native, once you're going from klibs into object files, then you're getting back into the native world. That's when you're native. So once you get the object files, which you can get if you build static framework from Kotlin Native, you're in native. That's when you get to native. Before that, you're in this hybrid space. So a similar question, this time already answered. What happens when we try to link all of these three klibs? And the answer is, if we are linking into static framework or library, it's fine. Because, as I mentioned, we are fine with unknown symbols in static and object files, because that's how they work. They are not linked, they are not ready to run, and they just know, I will need a symbol called hello world at some point when you're actually linking me. But we won't be able to produce either an executable or a dynamic, because we are missing the A. Whether A is dynamic library or it could be a static library too, doesn't really matter for this compilation process. But what is important is, if you remember, we gave cinterop just the header. Only thing it did is it took the header from C, transferred it into Kotlin IR, and then when we're building it again, Kotlin IR knows that this is actually a reference to a native symbol. So in the object file, it puts it as unknown reference that will be linked later. So we need something to link it against. There are ways to get around it. We will not be getting into them. You should not be doing that. And with that, with what you should not be doing, we get to common problems. I try to choose some of the more important ones. There are so many of them that we could be choosing all day. The first one is when you're depending on static libraries. Depending on static libraries by itself is fine. It's when you need to depend on the static library from two dynamic images, whether it's a library or an executable, it doesn't matter. So in this case, we have our foo. Foo will always, for reference, foo will always be the Kotlin in these examples, and then the main is supposed to be something on iOS, either an iOS app, macOS app, whatever. When I was doing a rehearsal, I realized that it would be better to make it easier to understand, but I'm hoping that this disclaimer is enough to make it easy to follow. And then the A can be essentially anything, any native thing, whether that's built by Kotlin somewhere, we don't care. Once it's native, it's native. So we have those two things, they both depend on a static library A. So what happens is both of them now include A1, A2. Those are the two symbols that we've been talking about some time before. Duplicate symbols, in very, very, very special cases, can be used. But most of the times, you don't want duplicate symbols. Some runtimes, like the Objective-C runtime, if you have duplicate symbols for classes, it will yell at you, it will warn you, but C itself may not. So if you have duplicate C symbols in two executables, you can have either undefined or very weird behavior. So it's important to never link a single static library into two dynamic images. You might be thinking, it's kind of like too simple, when does it apply at all, does it? And the thing is, usually this is resolvable, and you don't really care that much. But with Swift Package Manager and Kotlin Native, this is what often happens. Now, in this case, A is some third-party library. Let's call it Firebase. Firebase provides, because they want to be a good citizen, and this is how it should be done, so they want to provide support for multiple dependency management on iOS. So they provide support for CocoaPods, they maybe provide Carthage, I don't know, but they do provide Swift Package Manager as well. In Kotlin, because we can easily enough, consume CocoaPods dependencies, we would use their CocoaPods dependency, which would build a dynamic Firebase framework for us. So that's the A dylib. But then the iOS team, when they actually need Firebase as well, they will add it as a Swift Package Manager, because that's all the rage now. Swift Package Manager always builds to static unless it's a vendor framework. But Firebase, again, to be good citizens in the open source, are moving more and more into open source. So maybe even the whole SDK is open source now. So it will build as a static library. Now, our foo depends on a.dylib, which is supposed to have A1 and A2, but our actual executable has statically linked to the Firebase, which is the A1 and A2. So what can happen is you either will have linker errors that a.dylib doesn't exist, and it cannot find it. That's the better case. The other case is that it actually does link, and then it won't find those symbols in runtime because it expects them in a different dependency, in A and not in the main. There are two solutions, maybe workarounds. So the first one is that we actually don't depend on A from the Swift at all. And instead, we make it so that A is static, and we link it directly into our Kotlin framework and expose it ourselves. So that way, whatever your import shared, importing also Firebase, right? Your iOS developers will not like this. They don't like when that happens, because this is how it looks then. And imagine that the more implementation you put into your Kotlin, the more it will have to export. So in this case, A1, A2 would be the Firebase, and then you add some push notifications, so that's something you would need to export as well, and more and more. And now iOS people will just do import shared, and they have everything, all of the frameworks that they don't need, they don't want to care about. So the better approach is actually making your Kotlin into a static framework. So when you're configuring in build Gradle, you can configure whether it's going to be a static or a dynamic framework. If you configure it into a static framework, one, notice that we only need the header again. So we don't even need to download the whole Firebase anymore. We just need the header. We build into static, and then the Swift package manager, it builds or Firebase statically, and it builds our Kotlin and links everything together into one happy executable that has all of it, everything works, and your imports in Swift will look how you would expect them to look. Before Xcode 16, there was also a workaround where you could actually say that all of these symbols are going to be available at runtime. Do not worry about it. And we used it in Crash Chaos. Unfortunately, with Xcode 16, the stripping of debug symbols started to be a little better at its job, and it's stripping way more symbols than it would strip before, and that no longer works. So now, if you don't have the dependency, when it's stripping the symbols, it cannot follow it, and it's like, oh, we don't need that symbol. And then it only crashes in release once you send it to the App Store. So that's the worst thing. You build release for your phone, everything works. You're like, yay, let's send it to the App Store. And then you get rejected by the reviewer, and it's like, it doesn't run. The app crashes. And you take a look at the crash, and you're like, yep. That's because there's one extra step when you're building the installation, the bundle that you then deploy to App Store. That doesn't happen when you're just running release. So do not do that. Forget I told you about it. But it's good for debugging. Another issue that we often see is when you depend on any system library. Here I called out SQLite directly, because it's usually the library that this happens with. So in the last step, we decided, OK, we're going to be actually building our Kotlin as a static framework, so that we don't have that pesky issue. But we depend on SQLite, and object files, by default, don't know anything about the dependencies. They only know that I will need these symbols like this one, SQLite3 underscore something. So this is what you will often see when you're actually building the final executable, undeclared symbol. And you're like, the hell? And that's because it doesn't know that you want a different library and that you want a system library to link with. One way to solve that is the manual way, where you go and say, OK, I'm so sorry, iOS engineers, please put this into your other linker flags. We need this to be there. Or, which is the better one, you can actually use this auto-linking, where you can encode LD linker option into the object file. And then when the linker is running, it finds those, and it's like, oh, you actually want me to run with this linker option? Cool. And the linker option is, please link SQLite3, and it basically does this. It tells it, do that for me, everything's good. The last thing, it kind of captures the rest of the issues, I guess, and also the issues that I just talked about, is ignoring warnings, which then results into undefined behavior or unwanted behavior. One thing I want to stress, do not, under any circumstances, depend on static libraries from multiple dynamic ones. Whether that's a dynamic library or an executable, again, that's the same thing. The symbols will be included in both. At best, it's an undefined behavior, and it may work. Sometimes you will see these class is defined in both this and this. This is undefined behavior. And then your app runs, and you're like, it's fine. And then on one device, it actually loads in a slightly different order, and it starts crashing because it's accessing a different memory. So heed the warnings during the app startup. They are usually very important. I would like them to be errors myself. In closing, static linking is your friend. If you can, link statically. There are a lot of benefits in it, especially in Kotlin Native. Learn the native build process. It may seem like it's kind of abstracted away from you, but oftentimes, once we make a change or add a new dependency, we get these weird issues in the native build process. And if you don't understand it, you won't be able to resolve those. One more time, heed the warnings. And then, of course, have fun with it. Expect a lot of weird issues along the way. Reach out. I'm on KotlinConf and online anywhere. If you are doing KMP, I strongly recommend, no bias at all, not that I wrote it or anything, Sky, which will make your iOS developers like you more if you're on the Android side, because it will improve the API of your Kotlin Multiplatform framework. You can also wait for Swift export, but until that gets there, Sky can help you now. And a lot of people who use it actually got to us like, oh, this is actually good enough that we don't really have problems with the Swift side anymore. And I'm really glad to hear that every time. And then, as I said, I'm kind of terminally online. So follow me, reach out. If you follow me, I will probably follow you too, especially on Blue Sky. It's really easy to do. And thank you, everyone. And don't forget to vote.